Hello everyone, welcome to the ITLS Academy. Today we are going to discuss another topic in the series of FSSAI water analysis, and the topic that we are going to discuss is residual free chlorine and chloramines. Okay, so see what we have to see. We see that the water bodies, okay, in water bodies like your swimming pools and all, the free chlorines are added, and this free chlorine are known as a chlorination. Means that the addition of the chlorine into the water body. Now this process that is known as a chlorination is used to destroy or eliminate the microorganisms. Which type of microorganisms? The disease causing disease causing microorganism. It will be destroyed when this chlorines are added into the water body. That means that this chlorination also protect the water from the pollution. So in today's lecture we are going to discuss about that residual which are present into the water bodies. What we have to do, we have to take a sample and we examine that sample. Is there any residual of the free chlorine or the chloramines are present or not? So let's start today's lecture. Our first slide, that is your that is known introduction slide. Okay, now see, the chlorination of water supplies and polluted water serve primarily to destroy or deactivate the disease producing microorganisms. Okay, so the main aim of the chlorination is what? We have to destroy the or deactivate the disease causing microorganisms, and this chlorination is done to the water supplies and the polluted water. But for both of them, only the aim is what? We have to destroy or deactivate the disease causing microorganisms. And the another benefits of this chlorination is all that is your, when we treat the drinking water with the chlorine, it ultimately improves the quality of that water. Okay, which give a reaction of the chlorine with ammonia, iron, manganese sulfide and organic substances which are present into a drinking water. When this chlorination process occur, means that when we added the chlorine into that drinking water, then this chlorine are react with all these elements, that is your ammonia, iron, manganese sulfide and other organic substances, and it improve the quality of the drinking water. That's why this chlorination process is very important. A secondary benefit, particularly in treating drinking water, is the overall improvement in water quality resulting from the reaction of the chlorine with the ammonia, iron, manganese sulfide and some organic substances. Now come to the next slide, that is also about the introductive slide. Chlorination may produce adverse effect. Okay, if there is a benefit of the chlorination, on the other hand there is also a harmful effect of that chlorination which is very adverse. The taste and odor characteristic of the phenol and other organic compounds which are present into the water supply may be intensified. Sometimes this chlorine chlorine compounds are what? They are carcinogenic, and that compounds are what? That is chloroform. If it form, then it is carcinogenic. Now if this chlorine are combined and form a chlorination of the ammonia or amine bearing waters, they have a adverse effect on the aquatic life, so that to fulfill the primary purpose of the chlorination and minimize any adverse effect, it is very essential to proper testing of the procedure may be used, or knowledge of the limitation of the analytical determination. Okay, so that's why when we are doing a chlorination, we have to a proper knowledge about that process, and also identify that when we are doing a chlorination, it give a minimum adverse effect. Either it is to the aquatic life, either it is into the aquatic life or other human beings. Now come to the next slide. Chlorine applied to a water in its molecular or hydrochloric form. When we apply this chlorine into the water, now this will be applied into a molecular or a hydrochloric form, and initially it undergo a hydrolysis which form a free chlorine, and it consists of aqueous molecule chlorine, hypochlorous acid and hypochlorite ion. The relative proportion of these free chlorine form in pH and temperature dependent, and that pH of the most water hydrochloric chlorus and hydrochlorite ion will predominant. Okay, now come to the next slide, that is DBT colorimetric method. Okay, so for the determination of the free residual of the chlorine, we use a method that is known as a DPD method. Okay, now come to the principle of the DPD colorimetric method. That is your PD is used as a indicator. Okay, here the PD word is what? This PD word is used for a indicator, which means that to develop a color. So PD, which is used as an indicator in this method, the work of this PD is what? To develop a color. In the absence of iodide, and this free chlorines react with the DPD indicator. Okay, if the iodide ion are absent. Okay, so in that case, this free chlorine, what they do, they react with the DPD indicator. Okay, and instantly, and when this free chlorine react with the DPD indicator, it produces a red color. Substitute addition of a small amount of the iodide and act catalytically so that it causes the monochloramines, which produces the color. So this red colors are occur due to the production of the monochloramines. Addition of iodide ion to excess evoke rapid response from the dichloramine. Now the next is interference. See, when we perform any experiment, so there is a lots of interference which occur, and due to that interference, there is a error occur, and we does not get a correct result. So we have to eliminate that interference. So here the interference are what? Compensate for color turbidity by using sample to a zero photometer. Now there is a organic contaminant are there. This organic are what? They are act as a interference. Okay, contaminant means that the which is harmful for the experiment. Maybe produce a false free chlorine reading in most of the colorimetric method. Okay, so if there is a organic matters are there, then maybe it causes a false free chlorine reading when we take a reading from a colorimetric method. So maybe due to that presence of the organic matters, it causes a false reading of the free chlorine. Many strong oxidizing agent also interfere interfere in the measurement of the free chlorine in all the method. Such type of the interference like your presence of the bromine, presence of the chlorine dioxide, iodine, permanganate, hydrogen peroxide and ozone, they all are causes the interference when we performing the experiment. So we have to eliminate all these contaminant or all these elements. Now come to the next slide. However, when we reduce the amount of this compound, that is your bromide, chloride, iodide, manganese, iron, and oxygen in absence of other oxidant, it will not interfere into the experiment. Now, there are some reducing agent which are also interfere when we perform the experiment. That is your ferrous compound, hydrogen, sulfide, and oxidizable organic matter. They are what? They are not interfere during the experiment. Now minimize the chromate interference by using a thioacetamide black correction. Okay. Now the next is your minimum detectable concentration of the chlorine. So the minimum detection concentration of the chlorine is what? 10 microgram per liter as in the form of chlorine Cl2. This detection limit is achievable under a ideal condition. Normal working detection limit typically are higher. So 10 microgram per liter is the limitation of the chlorine concentration into the water body. If the higher concentration is detectable, then it means that our water body are what? They are polluted and it may be harmful for the human being. Now the next is your apparatus used for performing this experiment. So we required a photometric equipment, either spectrophotometer or filter photometer. Okay, if we use a spectrophotometer, then its wavelength should be 515 nanometer and it provided a light path of 1 centimeter or longer. And in the place of spectrophotometer, if we use a filter photometer, then it equivalent with a filter which having a maximum transmission in the wavelength range around 490 to 530 nanometer and it provided the path length around 1 centimeter or longer. So these two instruments are required for the performing this experiment, either spectrophotometer whose wavelength is 515 nanometer and light pathway is around 1 centimeter, and the second is your filter photometer whose wavelength is around 490 to 530 nanometer and light path is around 1 centimeter. Now the next is your glassware. Here we use a separate glassware including separate spectrophotometer cells. Okay, so for film photometer, both of the photometer, we use a separate glassware for free and combined measurement to avoid the iodide contamination in free chlorine measurement. The next is your reagent. So first reagent that we required is a phosphate buffer. So for this, what we have to do, we take a Na2HPO4 24 gram and 46 gram of unhydrated KH2PO4 and it will be dissolved into a 100 ml of the distilled water. Then again we take a 100 ml of the distilled water and we dissolve a 800 milligram of the disodium ethylene diamine tetraacetate dihydrate EDTA. Okay, first of all we take these two components and it will be dissolved into a 100 ml. Okay, 100 ml of the distilled water. Then we take a EDTA and again it will be dissolved into a 100 ml of the distilled water. Now we dilute it 1 liter of the dilute it with the help of the 1 liter of the distilled water and then we add a 20 milligram of the HgCl2 or in the place of HgCl2 you can also add 2 drop of the toluene so that it will prevent the growth of the mold. interfere from the trace amount of the iodide in the reagent can be negated by optional addition of that 20 milligram of HDCl2 to the solution. So this is the optional. Okay, if you add, then it will prevent the growth of the microorganisms. Okay, so here only for the preparation of the phosphate buffer we require these things. After the preparation of the phosphate buffer, we prepare a N diethyl dash P dash phenylene at a phenylene diamine, that is your DBD indicator. For this, what we have to take, simply we take a 1 gram of the DPD or 1.5 gram of the DPT sulfate pentahydrate. You can take any one of them. Either you take 1 gram of DBT oxalate, 1.5 gram of the DBT sulfate pentahydrate, or 1.1 gram of anhydrous DBT sulfate in chlorine free distilled water of 8 ml. Okay, so any of them you take it, either you take it DBT oxalate, DBT sulfate, or DBT sulfate. Okay, sulfate pentahydrate or DBT sulfate. Now you have to prepare a dilution of H2SO4 in the ratio of 1:3, which means that if we take a 1 ml of this H2SO4, then we have to take a 3 ml of the distilled water, and along with it we have to take a 200 milligram of the sodium EDTA. Then we have to make up a volume 1 liter with the help of the distilled water. Then we store it into a brown glass stopper bottle in a dark and discard when discolored. Periodically check the solution blank for the absorbance and discard when the absorbance at 515 nanometer exceed 0.002 per centimeter. In both of the reason we have to discard that solution if the solution are discolored, and if it show exceed 515 nanometer exceed 0.02 per centimeter. Now the next reagent that we required is a standard of the sodium thiosulfate of 0.1 normality. For this we take a 25 gram of this sodium thiosulfate pentahydrate, and it will be dissolved into a 1 liter of the freshly boiled distilled water and sterilize again a potassium dichromate. After at least 2 weeks storage, the initial storage is necessary so that it will allow the oxidation of any bisulfite ion. Now use boiled distilled water and few ml of the chloroform so that it will minimize the bacteria decomposition. That's why for the preparing of the sodium thiosulfate we use a boiled water so that it will minimize the bacterial decomposition. Along with it we also add a few ml of the chloroform, so it will also minimize the bacterial decomposition. Now the next reagent that we required is a standard of 0.1 normal Na2S2O3 by potassium dichromate. So for this what we have to do, we take a 4.904 gram of anhydride potassium dichromate K2Cr2O7 or primary standard quality in distilled water, and we dilute it for a 1 liter to yield a 0.1000 normal solution. Now we have to store it into a glass stopper bottle, and then we added at 80 ml of the distilled water with a continuous stirring and 1 ml of the concentrated sulfuric acid or 10 ml of the 0.1 normal of the this potassium dichromate, that is K2Cr2O7, and 1 gram of the potassium iodide. Now we leave that mixture for a 6 minutes in a standby position. Then we put it into a dark before sorry we put it into a dark by a standby position for a 6 minutes before titration. Then we titrate it immediately with 0.1 normal of the Na2S2O3. Titrate until the yellow color of the liberated iodine is almost discharged. Then when the yellow color are discharged, then we add a 1 ml of the starch solution and again we titrating it until we disappear the blue color. Then this, when the blue color disappear, then the final reading we get. So this is how we standardize that solution. Now after that we have to standardize the sodium thiosulfate titrate. For this we improve the stability of the 0.025 normal of the sodium thiosulfate by diluting an age of 0.1 normal solution, and we made it directed above with freshly boiled distilled water, and at same time we add a 4 gram of sodium borate and 10 milligram of the mercuric iodide per liter of the solution for accurate work sterilization and the solution daily in accordance with the direction given above using K2Cr2O7. Now the next is your procedure. So in procedure, the first part is that we have to calibrate the photometric equipment. For the calibration of the instrument with chlorine or potassium permanganate solution. Okay, so for when we have to calibrate the photometric equipment, we use either chlorine or potassium permanganate solution. So first of all, we have to prepare a chlorine solution. For this, we required preparing the chlorine standard. We required in the range of 0.05 to 4 milligram per liter from about 100 milligram per liter chlorine water standardized as follow. For this, what we have to do, we place a 2 ml of the acetic acid and 10 to 20 ml of the chlorine demand free water in a flask. Suppose that this is a flask. In a flask we added a 2 ml of the acetic acid and then we added a 10 to 50 ml of the chlorine demand free water in a flask. Then we added a 1 gram of the potassium iodide. 1 gram of that potassium iodide. We measure it into the flask a suitable volume of the chlorine solution. In choosing convent volume, note that 1 ml of 0.025 normal of the sodium thiosulfide titrate equivalent to 0.9 milligram of the chlorine. Then we titrate it with the standardized 0.02 normal of the sodium thiosulfide until that yellow iodine color disappear. Then we add a starch indicator into it and titrate it until the blue color are disappear. This is how this equipments are calibrated with the help of the chlorine solution. Now determine the blank by adding the identical quantity of the acid, potassium iodide and starch indicator to the volume of chlorine demand free water corresponding to the sample used for titration. Perform black titration A or B, whichever apply milligram chlorine or chlorine is equal to A plus B multiplied by N multiplied by 35.45, where N is equal to normality of the sodium thiosulfide and A is a titrated value of the sample and B is a titrated value of the plant. Now titrated value we find it like final volume which we get from the burette minus initial volume of the burette, that is known as a titrate value. Okay, now the next step is your use chlorine demand free water and glassware so that it prepare these standard developed color by first placing 5 ml of the phosphate buffer solution and 5 ml of the DBT indicator reagent in a flask and then adding 100 ml of the chlorine standard with through mixing as described below. Now fill the photometer or a colorimeter cell from the flask and read the color at 515 nanometer. Now what we have to do, we take a glassware. In glassware we add a chlorine demand free water and then we added a 5 ml of the phosphate buffer and 5 ml of the DBT. Now after that we have to add a 100 ml of the chlorine standard and mix it well. Now we fill that solution into the photometer or a colorimeter and take a reading at 515 nanometer. Now return the cell content to the flask and titrate with the standard FAS titrate as check on chlorine concentration. Now the next step volume of the sample. So use a sample volume appropriate to the photometer or colorimeter. The following procedure is based on using 10 ml of volume. Adjust reagent quantity proportionally for other sample volume. Dilute the sample with the help of the chlorine demand free water when chlorine exceed 4 milligram per liter. Now the next is your free chlorine. For this we take a 0.5 ml of each buffer reagent, and along with the buffer reagent we also take a DBD indicator reagent in a test tube or a photometer cell. Then at the same time we added a 10 ml of the sample into that photometer cell or a test tube in which the buffer reagent and the DBD indicator are already present. After that we add a color immediately, that is your A. Now come to the next slide. Monochloramines. Continue by adding one every small crystal of the potassium iodide, about 0.1 milligram, and mix well. If the dichloramine concentration is expected to be a higher, instead of small crystal, add 0.1 ml freshly prepared potassium iodide solution, 0.1 gram per 100 ml. Now read the color immediately B. Now next is your dichloramines. So in case of the dichloramines, continue by adding several crystal of the potassium iodide whose weight is around 0.1 gram. Okay, in monochromine, the weight of the potassium iodide is about 0.1 milligram. But here, when we prepare our dichloramines, then when we added this crystal of the potassium iodide, then its weight is around 0.1 gram and mix to dissolve. Let stand about 2 minutes and read the color C. Okay, so this is about the procedure. Now the next is your calculation. Calculation is what? Calculation is very simple. Free residual chlorine per milligram per liter is equal to A multiplied by dilution factor. A is what? A is a free chlorine. Monochloramines milligram is equal to B minus A, that I already told you what is B and what is A. Dichloramine is C minus B. So this is all about the determination of the chlorine by determination of the free residual of the chlorine by DBD method. I hope you will understand. But if you have any query related to this experiment, you are freely to ask me in a comment box, or for a further detail you can follow the ITLS Academy on different platform, that is your Instagram, Facebook, Twitter, YouTube, WhatsApp and LinkedIn, and subscribe our channel ITLS Academy on YouTube and get our app from a Google Play. You can also visit our website, that is www.itlsacademy.com, or ask your query to the helpline number that are already mentioned in your slide, that is 7080833450. Thank you for watching. Please like, share and subscribe our channel.